Welcome back to the lecture series. This is Dr. P. Srinivaslu, presently working as associate professor, North Shankar College. Video lecture series for probability theory stochastic process. So already we discussed about random process, giant density function, giant distribution function for random process. Now, today we are going to discuss about stationary process. What is a stationary process? Stationary means it is not varying with time. Now, whatever the random process we are going to consider, that is x of t, it's a function of time. This stationary random process, if we calculate its statistical properties, such as mean, correlation, and then moments, we calculate this variance. Now, it is independent of time. Then we can say that it is a stationary random process. Now, under this, first one is first order stationary process. If you observe this first order stationary process, now x of t is a random process, is a function of time. Now, corresponding density function, probability density function, fx of x1 comma t1. So, the corresponding density function, if you observe here, it is equal to fx of x1 comma t1 is equal to fx of x1 comma t1 plus delta t. Even there is a shift in time for any time t1, there is any shift in time. It is not a function of time. It is a independent of time. That means it depends upon the difference between the two intervals of time t1 plus delta t minus t1. So it is going to get that delta t change in time. It is not a function of time. It is an independent of time. Then we can say that it is a stationary process. Okay. Whenever it satisfies this condition, whenever this probability density function for random process, even it is not changing with time, it is a independent of time. Then if we calculate this mean value or expected value for this, now that expected value is a constant, then we can say that it is a first order stationary process. Now you observe this one, our assumption is this, there it is not function of time, it is an independent of time, even it is changed. So like it is a time invariant system. A time invariant system means the system is not going to be changed with respect to the time. Suppose the time the system is depends upon time, it is a time variant. It is not going to depends upon the time, it is invariant. It is also similar fashion. So even there is a different instance of time, we are considering this giant density function, probability density function. Now, the previous case and this case, both are same. Then, whenever it is satisfied, then if we calculate the expected value of that random process, it is going to be get constant. Now here we observe this one, x of t is a random process. I am calculating expected value. So this expected value of x of t is equal to integral minus infinity to infinity x into similar fashion like random variable. There is fx of x. Here it is a function of time. That is the only difference, dx. Now, if we consider another time instant in the random variable, in the process random process, it is one time instant. It is another time instant. So that is the expected value of xt. Nothing but expected value of x of t2 is equal to integral minus infinity plus infinity. You can write it as x1 fx of x, x1 t2. So the same random process, the random process signal is x of t, but the time instant is different. Here it is a t1, here it is a t2. So that's why x1 fx of t2 into dx1, similar fashion. Now we are concentrating only here. T2 is equal to, there is a addition of delay or there is some change in time. So T2 is equal to T1 plus delta T. Now, if we substitute this instead of T2 in that equation, expected value of T2 is T1 plus delta T. Again, if you see the formula, integral minus infinity plus infinity, x1 into fx of x1. Whenever there is a t, t2, that is going to be replaced with t1 plus delta t into, it is a dx1. Already for a first order stationary process, we assumed that whenever fx of x1 comma t1 is equal to fx of x1 comma t1 plus delta t, both are same, then if you replace this condition, then already it is a constant. Previously we have seen. So next one, if you consider at time instant t2 also, it is going to be constant. It is called, whenever it is satisfied, it satisfies the first order stationary process condition. Now coming for second order stationary process, the difference between first order stationary process and second order stationary process is the way of considering density function, probability density function. Previously, for first order stationary process, we have considered that the probability density function related to the random process is a fx of x only. Now here, if you want to, if you consider this joint density function, if you consider joint density function, then it is called second order stationary process. Again, the condition is same. Instead of considering a single probability density function, we are going to be consider a joint density function, means that is a two variables. There is a x1 only, here x2, fx of x1 comma x2 and corresponding x1 time instant t1, x2 time instant t2 is equal to fx of x1 comma x2. This t1 is replaced with t1 plus delta t. This t2 is replaced with t2 plus delta t for all values of t1, t2 and delta t. You remember here, previously there is a single density function, probability density function. Now there is a two probability density functions. That means two variables, joint density function. So the variables here, we are considering a two time instants. Previously, the time instant, and there may be some another time instant is a t2 delta plus delta t. Here time instants are same, but we are considering this giant density function. So whenever it is satisfies, we are going for a calculation of this correlation function. Whenever it is a R indicates that correlation function, and XX means autocorrelation function, means we are considering only one random process. So RXX of T1 comma T2, T1 comma T2 nothing but expected value of X of T1 into X of T2. So if we calculate this one, expected value of x of t1 into x of t2, the difference between these two time instants, t2 minus t1 is some tau. It is some constant. After calculation of this correlation function, if it is a function of tau, then it is a independent of time. Now we have tested the two properties here. One is a expected value of x, another one is correlation function. So these two statistical properties, if you see, in the first case, whenever we are calculating the mean value, whenever it is a constant, in the second case, whenever we are calculating the correlation function, it is a independent of time, then we can say that it is a wide sense stationary process. So next one is, see this one, wide sense stationary process. So whatever the random process x of t is a second order stationary process, is a second order stationary process means joint density function we need to consider here, joint probability density function. Then it is called wide sense stationary process. So the difference between stationary process and wide sense stationary process means, in the stationary process, whether we can consider a, a single probability density function or joint probability density function. But while coming for this wide sense stationary process, we are going to be consider only a joint density function, that is a second order density function. So it is called void sense stationary process or weak sense stationary process. Now, whenever the random process is a void sense stationary process, you need to test the following conditions. So again, the conditions are, you need to calculate expected value of that random process, x of t. So whenever if you calculate that mean value or nothing but expected value, it is equal to constant, it is equal to constant, that is one property. Another property, if we calculate the correlation function between two intervals t1, t2, that is going to be right, x of t1, x of t2. So expected value of x of t1, x of t2 is equal to rx x of tau. What is this t2? T2 is nothing but T1 plus tau. So, from T1, what is the delay? What is the delay we are going to be considering at different time instant? T1 is 1 millisecond, T2 is some T2, 2 milliseconds. So, the difference between these two is 1 millisecond. So, it depends upon that constant tau that is going to represent 1 millisecond, but it is not going to be depends upon that particular time instant. It is called wide sense stationary. Next, I'm going to stop this class. We'll continue the next class.